The Post Tower is the commercial headquarters for Deutsche Post WorldNet in Bonn, Germany. It is the result of a collaborative design process between architect Helmut Jahn, structural engineer Werner Sobeck, and environmental engineer Matthias Schuler of Transolar. The building serves as a representative platform for the company and thus needed to demonstrate a forward-thinking attitude, technological excellence, and maximum transparency. It is the symbol of the company's openness to new ideas and challenges. The glass tower is a result of this conceptual intention. Designed after an international competition held in 1997, it was completed in 2003 and is positioned between the city of Bonn and the gardens of the Lower Rhine Terrace beside the river. The form of the building points to the gardens and the river. Public space weaves through the site to connect the city with the terrace stairs and the ramps of the garden below. Along with two existing buildings, Lange Ungen and Deutsche Welle, the Post Tower is part of a scheme to redefine Bonn's city edge, creating both a symbolic and physical bridge between the city to the southwest and the Rhine River and gardens to the northeast. The angle of the building's curves responds to the prevailing southwesterly winds to minimize lateral loads. The building use group is business, and it is classified as construction type 1B. Since it is protected by a sprinkler system, the building was allowed unlimited height and floor area. Building organization. The tower stands 533 feet tall, housing offices and corporate support in 40 levels. The floor plate is very shallow, allowing most of the interior spaces to have a direct connection with the outdoors. The program is divided into two half-shell buildings positioned 24 feet apart. The floors are linked by two groups of glass elevators, presenting the visitor with views out to the city and the river. Curved corridors create very simple and clear circulation. Positioned at the elevators, connecting floors that cross the atrium space at every level link the two towers. At every 9th floor, a sky garden provides a communication and recreation space, as well as a marker for the vertical organization of the building. Meeting rooms, support spaces, and services are arranged toward the atrium, while the perimeter is lined with offices that all have views, natural light, and ventilation. The executive rooms are situated in the penthouse beside secondary mechanical support. Primary mechanical systems are housed on the 20th floor on a dedicated level where vertical systems can be run above or below with most efficiency. The climate in Bonn is characterized by wet, warm summers and long, cold winters. In an all-glass building, the changing climatic conditions must be carefully mediated. Overheating due to solar radiation and overcooling during the winters can be extremely taxing on traditional climate control systems. Compared to St. Louis, Bonn experiences slightly milder summer temperatures with a comparable relative humidity. Because Bonn does not experience excessive heat, there is less need to dehumidify. Structure. The conceptual intentions for the building were carried through in a structure designed to provide a framework for the glass enclosure. All structural elements are striving for maximum lightness, transparency, and clarity of expression. The primary structure comprises steel columns supporting concrete floor slabs. There are 19 columns in each half-shell building that transfer gravity loads to the ground. These are assisted by 4 concrete cores that resist compressive forces as well as lateral loads, acting as shear walls. Steel X-bracing connects the cores of the two halves of the building for stabilization. Steel outriggers at the middle of the building link the cores with the external support columns. This lends further stiffening to the primary structure. The one-way, poured-in-place reinforced concrete slabs distribute loads to the spandrel beams and columns, as well as provide a surface for the attachment of the double skin. Sky gardens at every 9th level are positioned above the X-bracing. The double skin is hung in 9-floor increments from these sky garden levels. The floor assembly depth has been minimized through the integration of many elements together. Each slab is a single pour for the joists and spandrel beams. The slab tapers at the perimeter to receive the facade connection. At this perimeter edge, the slab is only a few centimeters thick. At its thickest, the slab is 30 inches deep. This diagram shows the simple load paths of the structural members. The coffered slabs decrease the dead weight. A 30-inch floor assembly depth is very rare for a building of this type in the United States. As a comparable American example, One Bryant Park in New York City has a floor assembly depth of 57 inches. The post tower is more efficient in terms of material space. The one-way coffered concrete slabs organize the geometry of the offices and integrate the artificial lighting. In the corridor and central support spaces, the coffered slab is filled in to create a flat ceiling. At the level of each sky garden, the floor plates extend to provide structure for the attachment of the glazed enclosure on the building perimeter. Steel banana beams that run between the two sides of the building support the structural glass floors of the sky gardens. The form of the beams responds to the forces that are being transmitted along its length, keeping the bulk to a minimum. The transparency at the floor allows light transmittance to the atrium below. Enclosure. The enclosure has several main strategies: natural ventilation, daylight and solar energy, and intelligent shading controls to mediate between internal and external conditions. The facade structure is an example of complete integration between architecture and engineering, what the design team refers to as archineering. The size of glass panes is maximized while the structural profiles have been minimized almost to invisibility. The outer skin is hung in 9-story portions, allowing the use of very slender elements. The facade is adaptable, aiming to behave as a mediating skin between the external conditions and the desired internal comfort of the inhabitants. This skin is comprised of 2 fully glazed shells that allow natural ventilation, inhibit noise, and protect from the elements. The outer shell of the north face is flat, while the southern facade is shingled to allow better natural airflow when it is hot outside. Operable flaps at gaps between shingles in the straight north wall allow central control when desirable. The inner glass shell is double pane and user-operable. The outer glazing is a thick, argon-filled, thermally insulated glass. Building-operated louvered shades are placed between the 2 shells to mitigate glare and radiant heat gain. User-operated sunshades are located within each office space to enable individual control. Detail of south double-skin facade. Prefabricated primary facade, double-pane toughened glass, air cavity, and safety glass. Air intake grill. Wind needle, multifunctional cable, stainless steel tension rod, stainless steel cable stay, cast stainless steel reinforcing element, ventilation flap, in situ secondary facade. The enclosure is comprised of Pilkington OptiWhite clear glass, chosen for its low E properties, high transmittance, and clarity. It is a high-functioning glass used throughout the project. The 2 outer skins of the tower extend beyond the building plate to meet at a point at each end. This extension works as a windshield. The vertical stainless steel members supporting the hanging glazing are horizontally braced to resist shear forces. This allows the dimensions of the post section to be minimized, thus increasing transparency and natural light. The double low E glazing functions as a thermal blanket to create a buffer that increases the efficiency and effectiveness of the environmental control systems. In the summer, low E glass coatings work by reflecting light and heat away from the building, decreasing cooling requirement and costs. In the winter, the low E coating slows heat loss to the exterior, decreasing reliance on the heating system and running costs. Climate control systems. Breathing in the wind. Ventilation is provided from decentralized fan coil units at the building perimeter. These fan coil units, located at each office, bring 100% fresh air through the offices, into the corridor, and into the atrium space where it is released to the exterior through exhaust vents in the sky garden levels. The building uses 2 types of mechanical climate control systems: the FCUs, located at the building perimeter, and hydronic radiant heating and cooling. In the summer, water for the FCUs is cooled through a closed-loop heat sink piping system. This system carries warmer water from the building to the Rhine River, where heat is lost from the pipes to the river water. This cooler water, about 55 to 60 degrees Fahrenheit, is then returned to the FCUs to condition air at entry to the building perimeter. The water is cool enough that the building does not require a chiller at all. However, it is important to note that this temperature is not sufficient for dehumidification. Basic heating and cooling is handled through the integrated hydronic system in the coffered concrete slabs. Additional heat required by the fan coil units during the colder months is generated by a boiler in the penthouse of the building. Active systems integrated with passive ventilation and double skin. In the summer, air supply comes directly from the building envelope. Fan cool units cool air at intake, return air travels through Z-duct to Sky Garden, radiant cooling in slabs provides additional coolth. In the winter, the double skin functions as a thermal blanket. All air supply comes directly from the building envelope. Fan cool units heat air at intake. This air travels through the offices, under and over the glass partitions to the central spaces. Finally, return air travels through the Z-duct to the Sky Garden. Radiant heating in slabs provides additional heat. The base heating and cooling load is met by the radiant floors. The variable load, i.e. the flux in temperature that occurs at the skin, is met by the fan cool units or the FSL underfloor units. There are 2,000 individual FSL fan coil units in the post tower, supplying decentralized air to each office. Each unit has a conventional convector that allows fresh air to pass through from the double skin facade. The air is then conditioned and supplied to the offices. Air flows through the glazed office partitions to the corridor and into the internal rooms via displacement. The FSL units can be adjusted by the occupant of each office, allowing for individual control of airflow, heating, and cooling. Lighting. The integration of lighting and other building systems was important to the design team. Natural daylight is possible in almost all parts of the building due to the shallow building plate and complete glazing. Operable louvers can adjust daylight levels according to seasonal requirements and user preference. Artificial lighting is incorporated into the coffered structural beams that form the ceiling of the offices. The light projects upward and is reflected down into the spaces to reduce glare and maximize diffusely lighted area in the work environment. These light fittings were specially designed to integrate flush with the edges of the coffers. Additional can lighting toward the center of the plan provides more directed illumination. The artificial lighting is controlled by the daylight to reduce unnecessary energy use as far as possible. The building facade is lit up after dusk with light art by Jan Kersale. His intention was to create the perception of layering and transparency and a sense of life. The tower is backlit from the inside using exterior 200 and exterior 600 luminaries. The result is a dynamic light show that plays over the surface of the building from dusk to sunrise, exposing the double-skin construction and enhancing the architectural sense of transparency and reflection. Compared with a standard office building, the post tower is very efficient in terms of energy use for lighting and environmental control. This is largely a result of the extensive daylighting, solar thermal gain, and groundwater heat sink. Construction. Columns and floor slabs were constructed in two-level increments from the ground up at the same time as the interior concrete cores. The prefabricated primary facade was then attached from the bottom up to allow workers to complete interior finishes. The secondary facade was fabricated on-site and hung from the top down. Integration. The structure, enclosure, climate control, and lighting systems are extremely well integrated, resulting in a very coherent, efficient, and elegant building. Passive climate control and enclosure are unified. The windows are operable and direct ventilation is a key component of the climatic strategy. Active climate control and enclosure are unified. Decentralized FCUs bring in fresh air at the perimeter for conditioning of the interior environment. Passive lighting and active climate are unified. Building-operated louvers mediate sunlight entering the building. Active lighting and passive climate control are remote. Natural lighting and structure are unified. The structure was designed to maximize daylighting. Artificial lighting and structure are unified. The coffered structural slabs form the ceiling and are integral to the downlighting strategy of the purpose-made luminaries. Passive climate control and structure are unified. The concrete slabs and cores provide high thermal mass. Active climate control and structure are unified. The hydronic heating and cooling system is embedded in the concrete slab. The structure and enclosure systems are connected at the building periphery, where the structure of the enclosure system is hung from the concrete slab. The post tower is particularly well recognized for the collaboration of engineers and architects from concept to realization. The components seek to serve several purposes simultaneously, integrating the structural and performance requirements with the architectural expression. In Jan's words, perfection can only be achieved if nothing can be taken away.